Okay, chapter 3, classroom discussion problems. Problem number 6, we have two vectors, v sub 1 and v sub 2. Both magnitudes are given. And I just say units. If it's velocity, it should be meters per second, but it's not the point here. It's the vector algebra that we're going to focus on. You still have to keep track of units. Sometimes it's going to be milli, micro, centi. So you have to convert to System International first before doing any calculations. And direction is also given. For v sub 1, it is along the negative x-axis. For v sub 2, it is 55 degrees with respect to the positive x-axis. So direction and magnitude are given. You have to do the components for each vector and then add them up as vectors. I want to point out that the worst case scenario, the worst mistake that you can do, you'll add just 6.6 plus 8.5 and you say the answer is what? 14, 15.1. If you say the answer is 15.1, or you just subtract them as is, that's a horrible mistake. Do not ever add or subtract vectors like you do scalars. Okay, scalars, that's what you do in regular algebra. But for vector algebra, you have to do components, add those components, x with x, y with y, and then do the Pythagorean theorem, the strategy that we discussed earlier. So here's the first vector shown, once again, 6.6 units. And along the negative x-axis, this is the direction for my positive x in blue. And red color shows opposite direction. So right away you say x component for v sub 1 must be negative because it's pointing in the opposite direction. It should be clear that it's not just 6.6, it's a negative 6.6 for the x component of this vector. And what do you say for the y component? Do you see how vector v sub 1 in red is perpendicular onto the y-axis? And every time a vector is perpendicular onto a certain axis, its component on that axis is 0. So your two components for vector v sub 1 is negative 6.6 for the x component and 0 for the y component because it is perpendicular to that axis. V sub 2 in green, v sub 2 is 8.5 units and it's at 55 degrees with respect to the positive x-axis. Here's my positive x-axis, and this is my 55 degrees of an angle, and that's the v2 that is given, that we're talking about, and that's the vector we're going to solve, decompose into components. You can see there is a purple x component and brown-ish color for the y component. And you have to see that the x component is adjacent to the 55 degrees angle. And every time it's adjacent, there's got to be a cosine function to solve for the x component. You multiply the hypotenuse by the cosine of the reference angle, and you get a little less of a value. Remember, cosine cannot exceed 1, so if it's 8.5 as maximum, you're going to get something less than that, and it's positive. Okay, remember, it was a negative component for v sub 1. It's going to be positive component for v sub 2x. For v sub 2y, what do we see? If this is 55, Then the alternate interior angle here is also 55. Two angles are congruent. So the side is opposite to 55. And if the side is opposite, then the function is the sine. So it's still the hypotenuse times the sine of the reference angle. You still get a value less than that. And it's positive. Do you see how v sub 2y is pointing upwards, which is the same direction as the positive y direction? Positive y is up, v sub 2y is up, so v sub 2y is positive. And as I said before, you can always cheat a little bit and get the estimate for your vector sum using the parallelogram or triangular method, the graphical methods. And if you use the parallelogram method, when all vectors start from the same point, v1, v2, and you build the parallelogram based on v1 and v2 parallel, opposite sides are congruent and parallel. So v1, v1, v2, v2. Your diagonal is also the one that starts from the same point, the origin in this case, and the yellow vector is your vector sum. So what do you see? You see you're going to expect a little bit of a negative x component and some kind of a positive y component. And you're going to do the Pythagorean theorem once you get the components for both vectors. So v sub 1x, negative 6.6. V sub 1x, negative 6.6. V sub 2x, 4.9. 4.9. One is positive, the other one is negative. You add them up, and you get a negative 1.7, which once again makes sense, because if this whole thing is negative 6.6, then what you have is a positive, as a negative x component corresponds to a value that is less than 6, which is negative 1.7. Should make sense. And for the y components, what do we get? We get 0. We get 0 because v sub 1 is perpendicular to y-axis. And you get 7 because it's 8.5 sine 55 degrees. 7. A little bit of a note to be careful with sine and cosine function. You're probably going to use your calculators. And you have to remember that your calculators have two modes. The first one is degrees, DEG, something like that is going to be showing, and radians. And we're going to use radians later as well. So make sure that every time you calculate the sine or a cosine of a certain angle, you have the proper mode turned on your calculator. If you have 55 degrees, make sure your calculator is set to degrees. Later on, we're going to say pi radians, which is 3.14. And you have to switch to radians mode then. So be careful with the input on your calculator. So here's your net x component. Here's your net y component. Net means like the sum total of everything that you have. And your yellow vector represents a hypotenuse in the right triangle. You have negative 1.7 and positive 7. You really don't care for negative in terms of magnitude for the hypotenuse. So you just say 1.7 squared, throw in the negative, negative goes squared, still a positive, plus 7.0 squared. You get the magnitude for the sum is 7.2. which makes sense. See how it's really close to the value of 7. Yeah, it's a diagonal, so it's a little more than 7, but not so much more. Like, no, it's not like 14, right? It's just close to 7, so a little bit more, but that's what expected. And many students stop right here, and this is how you lose half credit. Because if the question is for vector sum, the keyword is vector, and vector has two things, magnitude and direction. So you have to specify direction. And what I like to do is I like positive angles. And I would rather deal with first quadrants rather than angles like 252 or whatever. I would rather choose this reference angle, and then it's just a positive 1.7, positive 7, and the inverse tangent that you call arctangent sometimes of the opposite over the adjacent gives you 76 degrees. If I were you, I would definitely check that my calculator, once you input this in your calculator, gives you 76 degrees, maybe 76 and change, but we're only dealing with 2 sig figs. It's 2 sig figs here, 2 sig figs there, 2 sig figs everywhere. So do not show me more than 2 sig figs for the magnitude and 2 sig figs for the reference angle. Now, if you'll flip-flop 1.7 and a 7, you should get an arctangent value corresponding to 14 degrees. And 14 degrees would be the angle that is the other angle. The total is 90, and if one is 76, then the other one is 14. If you choose this theta to be reference angle, you can't say 14 anymore. You have to go 7 over 1.7. On the other hand, if you choose theta to be this one, with respect to the vertical coordinate, then you have to say 14. Otherwise, it's a mistake, and you're going to lose points. So magnitude is not the end of story. You do the Pythagorean theorem, don't forget the direction. And the best way is to draw a sketch, specify a reference angle, and do the basic trig on those numbers that you get from components of a vector. Okay, some more practice, a little bit more advanced, because it's not just a plus b, but this time it's a minus. And see how a is multiplied by a scalar of 3. And you can ignore vector c, like it's just a diagram from the textbook, and you can do options b and option c here. I'm just going to go through b minus 3a. That should make sense, and then you can practice the other stuff on your own. So ignore vector c. We're not going to need it. So we're only going to work with vector a and vector b. Magnitudes are given. You have 44 and 26.5 units. Units are missing, which is unfortunate. Make sure you specify the units, or at least add them to your x and y coordinate system. And reference angles are also given. Make sure you keep track. I mean, this time you have to follow the reference angles. You can't change them anymore because you have the diagram to work with. So first thing first, a sub x, a sub y. What do you see? You see how a sub x is the side adjacent to 28 degrees angle. And if it's adjacent, the function is cosine. If it's a sub y, vertical component, if this is 28, then this is 28, alternate interior angles. and this side is opposite to 28 degrees right here. If it's opposite, then the function is the sine. Good news, both components are positive. It's positive towards x, it's positive towards y, so no need to add any negatives, both positives. And that's what we have for vector A. We just decomposed vector A into x and y components. For vector B, we got b sub x, and right away, what do you see? You see that the component is pointing in the opposite direction. Your positive x is to the right, and your b sub x is to the left, which makes it negative. And this side is still adjacent to 56 degrees, so now it is a cosine of 56 degrees, not 28. It was 28 for A, it's 56 for B. And it's a negative 14 and the change. The biggest concern is don't forget it's a negative, and make sure you don't flip-flop sine and cosine. If it's adjacent, it's cosine. If it's opposite, that's the sine. For b sub y, what do you see? You see that it's pointing towards upward direction, which is positive direction. So this component is positive. And if this 56, alternate interior is also 56, so this side is opposite to 56 degrees. And if it's opposite, the function is the sine. So it's positive, and it's a sine. And see, I'm keeping extra sig figs here. The amount of sig figs is 3, 3, 3, 3. And I'm keeping 4 sig figs because it's not the final answer. And I don't want my arrow to propagate. So I'm keeping 1 or 2 extra sig figs for intermediate calculations. Okay? B sub x and B sub y, A sub x, A sub y, they are not final answers. Those are just components. Now we're going to add them up or subtract. Doesn't matter. And once we get to the final result, the actual magnitude of b minus 3a, then we'll round it up to 3 sig figs. Yeah, you're not going to need C, vector C for this time, but just as a practice, I'm showing you that if you want to go C sub x, you see that vector C is perpendicular with respect to x-axis, and every time a vector is perpendicular, its component of that axis is 0. And if you want the vertical component, see how y goes up, vector C goes in the opposite direction, so it is a negative component. That gives you this value for C sub x and C sub y. Okay, it's not just a plus b this time. It's b minus 3a. And first, we have to deal with x components. So what's b sub x? B sub x is negative 14 and the change. Negative 14 and the change is b sub x. And you have to subtract 3 times a sub x. What's a sub x? A sub x is 38 and the change. 38 and the change, you multiply by 3. And it's going to be another negative number, so it's a negative, take away something, it's going to be even a greater negative value. So it is negative 131 and the change units. This is your x component only for that total vector that we are looking for. What about the y component? B sub y, let's take a look. B sub y is positive 21.97. B sub y, 21.97 minus 3 times a sub y. A sub y is 20.66. 20.66 multiplied by 3. It's a positive, take away another number, usually doing subtraction. And 3 times 20 is like 60. So 20 take away 60, that's negative 40. So makes sense. Both components turn out to be negative. That's perfectly fine. That means that the resulting vector is in the third quadrant, because the third quadrant, both sine and cosine are negative. Makes sense, right? So first of all, its magnitude, which is net x squared plus net y squared, net x squared, net y squared. Radical of the result gives you 137 units. Well, it is what it is. The main idea is don't forget to specify the direction. And for the direction, it's just third quadrant. It's not enough. You can be more specific because you know the components. This is your x component. This is your y component. If you want tangent, it's opposite over adjacent. Opposite would be your y. Adjacent is x. Negative and negative cancels out, and it's conveniently 16.9 degrees. Once again, if you have a calculator, check this input and see that your calculator shows you 16.9 if you want full credit on, quizzes, tests, and in real life. This is the final diagram. See how it's a negative 40 units for your y component and negative 131 for the x component. Oh, it's actually vice versa here. I'm so sorry. It is negative 40, which is here, and negative 131 is there. My bad. Because you have negative 131 as your x component. So negative 131 as negative x component. And negative 40 is your y component. So negative 40 right there. So this is the vector sum. It's still a sum because it's b plus minus 3a. See, the original a was north of east, and now negative 3 times the a has the opposite direction. And you multiply this 44 by 3 to get the value for the hypotenuse. So yeah, this is your parallelogram method, b plus minus 3a. And that's the diagonal for a parallelogram that you see shown is in dashed lines. Red vector for the second vector, and vector b is the first one. So b plus minus 3a, that's the parallelogram method. And this is your reference angle with respect to third quadrant, negative x-axis. Okay, projectile motion. How do I know? Because there is a ball, which is a particle, and it's thrown from the roof, and it lands. So what's going on? What's going on is what we call a free fall. You let it go, and the only force that acts on the ball is gravity. And gravity creates a free fall acceleration that we know the value and direction. So here we go. Let's sketch. the original altitude is given. It's thrown horizontally, so your initial velocity vector shows direction of motion, and the initial motion was horizontal, which is exactly shown with the red vector. So make sure you don't show me like some kind of an angle. If the problem says horizontal, then it's horizontal. If it's vertical, then you show vertical. If it's at an angle, then you have an angle. This time it's horizontal, and it lands 9.5 meters away from whatever that is, with roof of a building. So you know your X position for the time that you hit the ground. Good news, at that same time, your Y component is 0. Remember, when you hit the ground, your vertical position becomes your 0. And acceleration is constant, so we can use the two special equations, one for velocity, the other one for position. Once again, it's not necessarily just X, it can be Y, it can be Z. Any coordinate is good, and you'll get the same set of general kinematics equations. So, like I said, when you hit the ground, your Y position, vertical displacement, goes back to, vertical position, it's not displacement. Vertical position is 0. So it is 0. The initial position is given at 7.5. Initial velocity onto y-axis is 0. How is that so? Well, take a look at the vector that represents the initial velocity. This vector is perpendicular onto y-axis. And every time a vector is perpendicular onto a certain axis, the component of that vector on that axis is 0. That's why the y component, the vertical component of the initial velocity vector, is 0. Times the time, I say total time that it takes to travel through the upside down parabola and hit the ground. So the time to get from here to there. And then acceleration is free fall acceleration. And for y-axis, what do we have? The y-axis goes up for positive, and acceleration goes down. So it is negative 9.8 times the time squared. It's the same time that you have for the second expression. And you solve quadratic. And what's so special about quadratic equation? You're going to get two answers. One of them is probably 0, which makes sense because you start from 0 and you're at a certain position. Or it's even going to be negative, and you say, can time be negative? No, it can't. And you will end up with a single solution, which would be the correct solution to work with in terms of time that it takes to travel from the initial to the final position. So acceleration is opposite. Initial velocity is perpendicular. That's why you have 0 for initial velocity and negative 9.8 for the acceleration. Yeah, so I'm actually solving the equation and get 1.237 seconds. Well, imagine 7.5 meters, that's like 20 feet. And you throw something and you count 1 Mississippi, 2 Mississippi, and boom, it is already on the ground, right? So 1.237 is, something that you probably expect from such a free fall. And it's not negative, which is good news. So definitely something that you would expect. Now the question was for what's the initial speed? And initial speed requires, velocity equation. Direction is already shown, it's horizontal. But for the speed, we need to solve the position equation. The next thing that is given, what is given? It's given that it's at 9.5 in terms of the x-axis. So for my x position, at the time when we hit the ground, my position is 9.5 meters. And for the initial x, where do I start from? Initial x, I start from 0. It's 7.5 for the y initial, but it's 0 for the x component. So initial x is 0. Initial velocity for x, well, that's going to be just by itself because this is the whole component as is. There's no sine and cosine. It's just positive v sub 0. You might say that this is a cosine of 0. Okay, because for whatever the velocity vector here, you would be talking about component that is adjacent, and the angle between the component itself and vector is just 0. And if it's adjacent, it's cosine. Cosine of 0 is 1. So you get v sub 0 as is. That's what we are looking for. Times the time, which we already know. Time is 1.237. Plus 0. Why is it 0? Let's take a look at the acceleration. Acceleration vector is perpendicular onto x-axis. Every time a vector is perpendicular onto a certain axis, its component on that axis is 0. So acceleration onto x is 0. And that's it. You solve for the initial velocity onto x-axis, and this turns out to be the total initial velocity because it's all horizontal, no vertical components, no need to do any Pythagorean theorems. It's just 7.7. End of story. So once again, there's always a position equation and the velocity equation. Depending on what's given, depending on what's missing, you set up the system of two equations, see what's given, see what's missing, and solve with either substitution or elimination. Just be careful with vectors, because vectors can be positive, negative, or if they're perpendicular onto a certain axis, then the component is 0. I think it's the last one for today. So one last push, number 22. This is your general scenario for any kind of a projectile motion. When you have an initial velocity at an angle, so it has both x and y components, and trajectory is a parabola, upside down parabola, and there is an acceleration that is a free fall acceleration of 9.8 facing downward towards the center of the Earth. And once again, it doesn't matter what's given, what's missing. We say acceleration is constant, and we're going to use two equations, one for velocity and one for position. And the tricks are the same. When you reach the maximum altitude, what do you say? You say your vertical component of the velocity is 0. Momentarily, in the vertical direction, you stop. You never stop in the x direction, but y direction, see, it was a positive, less positive, less positive, and once you hit the topmost point, you get the 0 value for the vertical component of the velocity. And then you hit the ground. What's so special about hitting the ground? Your vertical position is, once again, 0. Sorry, my 0 is missing on the diagram. Well, the origin is shown as an intersection of two axes. So this is the 0, and you land on the ground. X is not 0, but Y is 0. So Y is 0. Y is 0 when you hit the ground. Your initial position is also 0 in terms of Y. Your initial velocity, the Y component, would be the sine function, because we're talking about the side that is opposite to theta. If this is theta, then this is theta. Alternate interior angles are congruent, opposite to theta, sine function. So v sub 0 y times the time that it takes to go from the initial to final. And the acceleration is a negative free fall, because y goes up and it's positive, and acceleration goes down and it is negative, times the time squared. So you plug in what's given, what's missing, boom, you solve for the vertical component of the initial velocity. So you know this value. Yeah, once again, if this is theta, then this is theta, and this side is opposite to theta. So this is a sine, and this is a cosine. Solving for the position equation with the initial velocity now being known from the previous calculations, 9.27, you plug in here, you solve for the time. It's a quadratic equation, and you have the first answer as 0. The first answer is 0 because you are at 0 when time is 0. And the second answer, you are at 0 when time is about 2 seconds. That's it. We will discuss relative motion in the second part of lecture. I'm gonna pause the recording, stop the recording, and we'll continue next time.